Hey everybody, this is Mr. Parliament, and this is a video tutorial that I'm making for solving problem 7 on worksheet 2. When I ask you guys to submit your answers for either question 6 or question 7, the majority of you guys chose question 6, so I'll post some of those answers on the website for you guys to look at. Question 7, I think, was more of a struggle. There were a lot of people who had a good start, kind of got partway there, but were struggling at doing the torque balance. As of right now, as I'm making this video, I've gotten one submission for question 7 that got to the correct answer for the coefficient of friction. A lot that kind of had partway there, but didn't quite get to the right answer. The correct answer that I did receive is a valid solving method, but I thought it was a little bit strange how the student got there. So I figured I'd show you my reasoning and then talk a little bit about that other solving method and why it works. So first of all, here's a picture of our ladder. We've got gravity pulling down on the ladder at the center of the ladder. We've got the force from the wall pushing to the left on the ladder. We've got friction counteracting that. Friction would keep the ladder from sliding this way. If the wall is pushing to the left, friction has to push to the right to keep the ladder from sliding. And then we've got normal force pushing straight up. Normal force, remember, is always perpendicular to a surface. So it's going to push the ladder straight up. Now I noticed that on the worksheet, if you open it up in Word, Microsoft Word, it shows you this picture, but if you open it up in Google Docs, it doesn't. So I apologize if you didn't have this picture when you were working on question 7. It was supposed to be part of the problem. All right, so before we can start solving the problem, we need to find what these angles are. Because if you recall, torque is equal to, and I'll go to the next slide here for a second, torque is equal to the force times the radius times the sine of the angle. So in all the previous problems, we had 90-degree angles between our lever arm and our force. And 90-degree angles are nice because the sine of 90 degrees is 1. But now we're going to have angles that aren't 90 degrees. So in order to solve for those angles, I called theta 1 the angle from the ladder to the ground. I called theta 2 the angle from the ladder to the force of gravity, which is pointed straight downward. And then I called theta 3 the angle from the ladder to the force from the wall. All right, so for solving for theta 1, I used the fact that the tangent of an angle is equal to the opposite side of that triangle divided by the adjacent side. You have all three sides, so you could use sine or cosine. I just use tangent. So tangent of theta 1 is 4 over 3. So in order to get theta by itself, we take the inverse tangent of both sides. So theta 1 equals the inverse tangent of 4 over 3. And if you plug that into your calculator, it will give you 53.13 degrees. Now, you might be more used to calling this arctangent in your math class. Arctangent and this tan to the negative 1 are the same thing. They're both the inverse tangent. It's important to note here that the to the power of negative 1 is not the same as saying 1 over the tangent of 4 over 3. So I think that can get a little confusing. All right, so there's theta 1. Theta 2, we can actually just solve by the fact that we have a triangle right here. The force of gravity points straight down, so it's going to be at a right angle to the floor, so we have a right triangle. And you guys know that if you add up all of the angles of a triangle, it equals 180. So theta 2 must equal 180 minus this angle of 90 degrees minus this angle of 53.13 degrees. And that gives us 36.86 degrees. Theta 3 actually ends up being the same as theta 1. And I forget the official name of that angle theorem, but I've always called it the Z theorem. That's how it was taught to me. And the Z theorem states that if you have two parallel lines and the force from the wall is in fact parallel to the floor, and you have a diagonal line connecting them, this angle right here is the same as this angle. So theta 3 equals theta 1, which is 53.13 degrees. All right, so we have all three of those angles that we need. All right, on to the next page. So I've redrawn the picture here. I've now written in those three angles that we need, and I put a couple of distances along the ladder. So the force of gravity is going to act in the middle of the ladder, so that would be 2.5 meters away from the pivot point if it's a 5-meter long ladder. The force from the wall is all the way at the other end of the ladder, and that's at 5 meters. So I chose the bottom of the ladder as the pivot point, and my reasoning there is that if the ladder started to fall, it would pivot about that point. Because it's not falling, because the ladder isn't rotating, you can actually choose any point along the ladder as your pivot point. And the reason for that is since it's not rotating about any one of those points, the sum of the torques about any of those points should be 0. All right, so first off, I'm going to go ahead and calculate what the force of gravity is, and it tells us that the force of gravity is m times g. You guys know that. So force of gravity is m times g. I used 10 for gravity, 10 newtons per kilogram, because I wanted to make the math a little easier. I figured there's already a lot of complicated stuff in this problem. And 25 times 10 gives you 250 newtons. I believe that if you use 9.8, you get something like 245 newtons about for the force of gravity. All right, so the sum of the torques about that pivot point is going to be equal to 0. And our first two torques are actually going to be 0. The torque provided by the normal force is 0 because it's right here at this pivot point. It's at a radius of 0 meters from the pivot point, so anything times 0 is 0. And the force of friction also has a torque of 0 because it's also 0 meters from the pivot point. So those first two torques you don't have to worry about. As far as the torque caused by gravity, well, the force of gravity is 2,500 newtons. The radius for that force from the pivot point is 2.5 meters. And then the sine of the angle, that would be sine of 36.86 degrees. Running out of battery. Let me plug in my computer real quick. All right. So that equation is just the equation for torque of force times the radius from the pivot point times the sine of the angle, where the angle is the angle from the lever arm to the force. I called that a negative torque because that force would tend to rotate the ladder clockwise, and clockwise is negative. Our next torque is the torque caused by the force from the wall. And that one would be positive because it would tend to rotate the ladder counterclockwise. And that would be equal to the force from the wall, which we don't know yet, times the radius from the pivot point, which is the full length of the ladder, 5 meters, times the sine of the angle between the force and the ladder, which is 53.13 degrees. All right, this little symbol before, if you haven't seen it, just means therefore. So therefore, I can rearrange that equation to solve for the force from the wall, which would be the force of gravity, 250 newtons, times 2.5 meters, times the sine of 36.86 degrees. And divide that by 5 meters times the sine of 53.13 degrees. Plug that into your calculator, you should get a force from the wall that is 93.7 newtons. All right. So we've solved for two new forces on this slide. We solved for the force of gravity by just doing m times g, and then we use the sum of our torques to solve for the force from the wall. The sum of the torques equals 0 because the ladder isn't rotating. All right. So on this last slide, remember we started off with trying to find the coefficient of friction, and I put up the equation that the force of friction equals the coefficient of friction times the normal force. We can rearrange that to solve for coefficient of friction as just the force of friction divided by the normal force. All right, so I've got the picture up here again, and now I've written in those two new forces that we know. We know that the force from the wall is 93.7 newtons to the left, so I called that negative 93.7 newtons because in the x direction we always call left negative. And then for the force of gravity, I have negative 250 newtons. Again, I called that negative because typically down is the negative direction. All right, so now we're actually just going to do a sum of the forces. We know that the sum of the torques is 0 because it's not rotating. We also know that the sum of the forces is 0 because the ladder isn't falling straight down or accelerating left or right. It's just staying there. All right, so the sum of the forces in the y direction is going to be equal to the normal force plus the force of gravity. And that's going to be equal to 0. So the normal force is the unknown here. And then you add to that the force of gravity, negative 250 newtons, and that all equals 0. So if you solve for normal force, that's 250 newtons. The sum of the forces in the x direction would be the positive force of friction, because that's pointed to the right, plus the negative force from the wall, 93.7 newtons. And again, that adds up to 0, because it's not accelerating left or right. So plug in your force from the wall of 93.7 newtons, solve for force of friction, you get positive 93.7 newtons. All right, so we've got both the force normal and the force of friction. So the coefficient of friction is going to equal 93.7 newtons divided by 250 newtons. The newtons cancel out, and that leaves us with a coefficient of friction equal to 0.37. And that coefficient of friction is unitless, the newtons, because the newtons cancel out. All right, so here is the solving method I wanted to talk about. This student did not use any trig functions, did not have to do the sine of any angles, but still got to the correct answer. And it took me a little while to figure out why, but what I realized is that they didn't deal with the total length along the ladder. For the force from the wall, they used this vertical height of 4 meters right here. And for the force of gravity, they used half the distance to the wall. So half of 3 is 1.5. So the reason that gets you the same force of friction and therefore the same coefficient of friction is because the sine of 53.15 times 5 is going to be 4. And that has to be true because that's actually how we found that angle. Additionally, the 2.5 meters halfway up the ladder times the sine of 36.86 degrees is going to get us 1.5 meters because we actually used this triangle right here in order to find that angle. So that's why it does work to use that vertical height and that horizontal distance as your R values, because that's essentially taking into account the sine of the angle. So if that solving method makes sense to you, it does get you the same answer. Although it's a little bit more mathematically complicated, I think in my mind it's a little easier to follow what our radius will be if you use the radius along the ladder and make sure to include the sine of the angle that you're dealing with. All right, so there's that one. I know that this is a tricky question. I do think question 7 is easily the hardest problem on the worksheet. I think it's kind of one of the harder problems we do all year. So if you have any questions about the solving method, please email me. The assignment for Friday the 27th, which you probably will be watching this video tomorrow, so Friday, is to do the other problem that you didn't solve. So if you did problem 6, I want you to work through problem 7 and see if you also get 0.37 or 0.38, depending on rounding error. And if you did problem 7, revisit your answer based on this work and give problem 6 a try. And you're welcome to check out the keys that I post online. All right, there's that tutorial. Have a great rest of the day, guys. Thanks, and bye.